Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In this class, we plan to discuss on level triggered and edge triggered circuits. In the previous sessions, we discussed about sequential circuits, also about the flip-flops and latches, which are built on the concept of sequential circuits. Let us recall the block diagram of the sequential circuit. It contains a combinational circuit to which the memory is connected. The inputs and the memory elements together determined the output state of the circuit. Then we designed the various types of flip-flops and latches based on this concept. Hope you remember how flip-flops differed from the latches. Let us have a look at this diagram to recall the differences. The latches lacked the clock pulse and flip-flops worked on the triggering of clock pulses. Triggering means you are making something happen in the circuit, or in other words, we are controlling the circuit using certain signals. And here we use clock pulses to trigger the circuits. Now, what are clock pulses? They are signals with changes in the voltage occurring at regular intervals. Since the clock pulses are discrete and occur only at regular intervals, their performance is stable. Or we can say that the next change of output can be predicted. This aspect is very crucial in the making of certain electronic devices. And how latches are working? They change their output as and when the inputs to their circuit is changed. So, their next change of output cannot be predicted. And why are we talking about all this again? It is because you are going to learn about how and when triggering is done in flip-flops. So, this session focuses on level triggered and edge triggered circuits. Also, we will discuss on master slave flip-flop, which is an edge triggered flip-flop. Let us understand the difference between level triggered and edge triggered first. First of all, you should understand the difference between level and edges. Look at this diagram. You can see a blue line which is a signal going low for some time and changes to a high state later. So, there are two levels for the voltage, either high or low. When it is at low voltage or at low level, it can trigger a circuit. Similarly, when the signal is at high voltage or high level, it can also trigger a circuit. If a circuit is triggered when the signal is at high or low level, it is known as a level triggered circuit because only the two level high and low has the power to trigger these circuits. The latches are a good example of level triggered circuits, and it is the simplest way to control the circuits. Now, you must be curious to know about the edge triggered circuits. We already told that the signal has two levels, high and low, and if the circuit is triggered during that levels, it becomes level triggered circuits. What else is remaining in that signal? Let us look at the diagram again. I have labeled one more place in the signal. Look at that, it is known as the edge of the signal. What exactly is an edge then? It is the transition of the signal from the low level to the high level or from the high level to the low level. The former is known as rising edge or the positive edge, and the latter is the falling edge or the negative edge. See this diagram. Now, you can clearly make out the rising or the positive edge from the first part of the figure and falling or the negative edge from the second part. The clock pulse shown here is a square wave signal. The flip-flops are edge triggered circuits. They can be triggered at the positive edge or negative edge of the clock pulse. You can make out from the block diagram whether the flip-flop is a positive or negative edge triggered flip-flop. If you can notice only an arrow depicting the clock pulse, it is a positive edge triggered flip-flop. Or if you find a circle attached to the bottom of the arrowhead of the clock pulse, it is a negative edge triggered flip-flop. You might have observed that the clock pulse is changing its levels at discrete intervals which are of the same duration. This explains the reason for the flip-flops being stable in predicting their next stage of output. Now you learnt the difference between these triggering methods, the level triggered and the edge triggered. You should also note down one more difference, that is, level triggered circuit changes their output during an entire half of the cycle, and in the case of edge triggered circuits, the output changes at only one instant during the clock cycle. To comprehend this better, look at the figure. You can see the clock duration. A clock period is measured in time from the start of the one positive edge of the clock to the start of the very next positive edge of the clock. In this duration, half of the time the signal is in high state or low state, whereas the edges appear only for an instant of time. You can still streamline the process of changing the output in the circuit. Due to the nature of elements used to build these logic gates, there are some undesirable effects such as instability if the circuits can change their outputs for almost during their entire half of the cycle. These issues are out of the scope of this syllabus, hence we will not be discussing in this class. So, it is better to change the output of the circuit during the positive edge or at the negative edge of the clock pulse. And the flip-flops which are triggered during the rising or falling edges are called as edge triggered flip-flops. Let us see an example for an edge triggered flip-flop. In edge triggered flip-flops, output change occurs only at that specific level of the clock pulse, after which the circuit becomes unresponsive to further changes and is locked out. This defines stability to the change of output and highly recommendable for the synchronization purposes. Let us see an edge triggered D flip-flop. It has three basic flip-flops which are marked as 1, 2 and 3 respectively. The first flip-flop has NAND gates 1 and 2. The second flip-flop has NAND gates 3 and 4, and the third flip-flop has NAND gates 5 and 6. The output of the circuit is provided by the third flip-flop, which is an SR latch. To understand the working, you need to recall the truth table of SR latch built by NAND gates. When S equal to 0 and R equal to 1, the output goes to the set state, and when S equal to 1 and R equal to 0, the circuit gets reset, and when both inputs are high, the circuit remains in its previous state. Now, here there is only one input D, so it can assume only 2 raised to 1 combinations, that is 2 inputs. It is when D equal to 0 and D equal to 1. We need to also analyze these cases when clock is at high and low states too. Let us start with the first case, clock equal to 0 and D equal to 0. Since the inputs at the gates 2, 3 and 4 are 0, the outputs at these gates will be 1. It is because as per the truth table of the NAND gate, if any of its input is 0, the output of that gate will be 1. Now, what about the first gate? It has 2 inputs. One is the output of the second NAND gate and the other one is the output of the fourth NAND gate. Both values are 1 now, which produces a 0 at the output. Now, you have S equal to 1 and R equal to 1, which is the input to the SR latch. We all know that when the SR latch has both of its input in the high state, it will continue to remain in the previous state. Now, assume that suddenly the clock pulse becomes 1. Then what happens? the gate 4 still has 1, but to analyze the outputs of third and fourth gates, we need to check the previous state values too. The gate 3 has its 3 inputs as 1. One is the clock pulse, which is now 1, and then it has the output of the fourth gate, which is now turned out to be 1, and the third input is from the previous value of the second gate, which is also 1. This produces a 0 at the R input to the SR latch. What about the second gate? It has the clock input as 1 and the previous value from the first gate as 0, which produces a 1 at the output. So, the S input to the SR latch becomes 1 now. This is enough to determine the output of the circuit. What happens when S equal to 1 and R equal to 0 in the NAND gated SR latch? The circuit turns to the reset state with Q equal to 0 and Q dash equal to 1. So, when the clock pulse becomes 1, the state of the circuit changes. Now, the clock pulse will be turning back to 0. You can guess the state of the flip-flop. It will set the inputs of the SR latch to 1 again and will continue to remain in the previous state itself. At this state, now the flip-flop's output is changed. That is D equal to 1. Now, the clock pulse is still 0. Now, what will be the states of NAND gates 1 to 4? Since the clock pulse is 0, it will turn the input NAND gates 2 and 3 to 1. This will in turn change the inputs to the SR latch as 1 again. We can ignore the outputs of the NAND gates 1 and 4 since we have got the input values for the SR latch. What happens when the NAND gated SR latch has both of its input as 1? It will continue to remain in the previous state. This output will help us to reinstate that even though the inputs to the circuit changes, the flip-flop will be still in an unresponsive state as long as the clock pulse transmits from 0 to 1. Now, let us verify the last part, that is when the input to the circuit D is 1 and the clock pulse is having a transition from 0 to 1. What happens to the circuit now? Since the external inputs to the circuit are 1, it has to check the previous state values. Earlier, when clock equal to 0 and D equal to 1, the input to the R gate was 1. Since inputs to the NAND gates are 1, the output of the fourth NAND gate will be 0. Now, this 0 will be fed as an input to the third gate. Since the value is 0, it will definitely produce a 1 as its output. That means, the R input to the SR latch has the value 1. What about the second gate? To know the output of the second NAND gate, it should know the output of the first NAND gate in the previous state. Previously, it was 1. Now, both the inputs to the second NAND gates are 1 again, which will produce a 0 as its output. Now, we do not have to bother about the first NAND gate as we have got the inputs to the SR latch. What are the values of S and R in this case? S equal to 0 and R equal to 1. Such a state will set the circuit to have Q equal to 1 and Q complement equal to 0. By this time, the clock pulse will turn back to 0, causing the circuit to retain in its state. This process will continue and we can infer that when the clock pulse moves from low to high, depending on the value of D, it will set or reset the circuit, and when the clock pulse reaches high level and goes back to the low level, no change happens to the circuit. When again the rising edge goes up to 1, the process continues and will produce the output depending on the value of D. Now, let us have a look at the timing diagram of the positive edge triggered flip-flop. Look at the clock signal. At its positive edge, dotted vertical lines are drawn to indicate that the triggering happens at the positive edge. Also note that the clock pulse is changing at regular intervals of time. Now, turn your attention to the next signal in the diagram. the D input, it is not uniform as the clock signal is. Now look at the last line in green color. This is the output of the D flip-flop Q. Observe it closely and understand that the Q remains 0 initially even when the D input signal is at a high state. As per the characteristic table of D flip-flop, it should go to a high state when input is high, but it did not happen. Why? Because the triggering did not happen. The clock was at the low level. When the clock moves from low to high, depending on the D value, you can see that Q also changes. It goes to the high state and continues to remain in the state till the next rising edge. Take a special note that the input D dipped to 0 in the middle of high level of the clock pulse, but our flip-flop did not respond to that. It continued to remain in a high state. Now see, the next rising edge has come. Now you can expect a changeover in the output because D has turned to 0 already in the previous cycle. So, your output Q falls down to 0 and this value will be locked in the flip-flop until the next rising edge. Now, we are on the third rising edge. What is the value of D? It is high. Now, what should happen to Q? It should move to a higher level and it did. It remained in that state till the next rising edge. Here, D was 0 at that time and the output Q dipped to 0 at the falling edge and will continue to remain the same till the next rising edge. Now, you should carry these two things in your mind even though your input signals was not showing a uniform pattern. The output was not like that. It changed only at the regular intervals of time. That is why we were saying that the flip-flop's change of output is predictable. Now, it is very clear in the diagram and we are very sure at what time we can expect that change of output. The second thing is the flip-flop become unresponsive for most of the duration of the clock cycle and change its output only at an instant of time. This will help the circuits which are built using these circuits to synchronize with other circuits. We are not elaborating on the synchronization of the circuits here as it is not covered in the scope of this course. Now, shall we have a look at the timing diagram if the flip-flop was negative triggered? The straight vertical lines shows that the flip-flops are triggered at the negative edge. And if you observe the diagram, then you can make out that the output Q given in blue color changes its state only at the negative edge transition. With these concepts, we are winding up the session on the edge triggered flip-flops. To summarize, here we differentiated the level triggered and edge triggered devices. Then we discussed about the two types of edge triggering, the positive edge triggering and negative edge triggering approaches. Finally, with an example of the D flip-flop, we learned how an edge triggered flip-flop works. To understand the working better, we discussed the timing diagrams too. In the next class, we will continue with the triggering of flip-flops using a special type of flip-flop known as master-slave flip-flop. Thank you for watching. See you in the next session. Bye.